So the definition of a vector space, let's define it. So a vector space, and I'll underline it here to indicate the term that I'm defining. So a vector space over the field F is a set V, and we'll reserve this notation V here. So for this course, V, capital V, always indicates a vector space. So it's a set V with two operations, plus and a scalar multiplication, that satisfy a number of properties. First off, we require the addition to be defined for any two elements of the vector space. So given a u and v, then u plus v has to be defined, and it also has to be again back in the set that we specified. Also, given any vector u and any scalar lambda from the field, we require that the scalar multiple be defined and also be an element back from that vector space. So together, these two are referred to as the closure properties or closure axioms. So we say it has to be closed under addition and closed under scalar multiplication. We also require that u plus v is equal to v plus u, so the addition is commutative, and the addition needs to be associative. So if I add u to the sum of v and w, that has to be the same as u plus v added to w. There also needs to exist an element in v that has the magic property that if you add it to any element of v, nothing happens. So that's the additive identity. And there needs to be the property that for any given element v, there has to exist a w with the property that v plus w gives you the additive identity. So you have to be able to get back to the identity. And that's the inverses, additive inverses. So these properties together tell you that v is what's called a group in the technical mathematics sense. And this first property right here tells you that v is an abelian group. That's another term for commutative when you're talking about groups. We also require the multiplicative identity property to hold. So if we take the multiplicative identity 1 from the field and you multiply it against v, nothing happens. And it also needs to be the case that if we take any two field elements and we take any two elements from v, then they satisfy the distributive property in both possible senses. So that is, the scalar multiple of the sum of two vectors needs to distribute. And also that the scalar multiple by a sum of field elements needs to distribute. So the difference between those two is where the addition is taking place. All right. And now that we've got that big awkward definition of a vector space, we can go ahead and say what a vector is. So in this class, a vector is the name for an element of a vector space. So we'll be talking about vector spaces of lists of numbers, or n tuples, the familiar sort of prototypical case of Rn or Cn. Those will be vectors, but also if our vector space is a vector space of functions, then our vectors will be functions.